Next, we turn to IS entity concept.
I'd like to introduce CSA enclosure ratings and intrinsically safe apparatus. CSA enclosure ratings are defined in CSA C22.2, number 94. They are similar to NEMA ratings and are designated by type numbers, such as type 4. Previously, they were designated with the prefix CSA-ENC, such as CSA-ENC4. Next, intrinsically safe apparatus must be installed with barriers that limit the electrical energy entering the equipment. There are two methods for determining acceptable combinations of intrinsically safe apparatus and connected associated apparatus, such as barriers, that have not yet been verified as a combination: the entity concept and the system parameter concept. The entity concept specifies 4 parameters: voltage, current, capacitance, and inductance. Additionally, please note that because cables themselves have energy-storing characteristics, the length of the cable connecting intrinsically safe equipment and associated equipment may be limited.
I'd like to introduce the 4 parameters used in the entity concept of intrinsic safety. The values defined for the intrinsically safe apparatus itself are Vmax, Imax, CI, and Li. Vmax refers to the maximum voltage that may safely be applied to the intrinsically safe apparatus, and Imax refers to the maximum current that may safely be applied to its terminals. CI is the internal unprotected capacitance of the apparatus that can appear at the terminals under fault conditions, and Li is the internal unprotected inductance that can appear at the terminals under the same conditions. Barriers used with intrinsically safe apparatus must satisfy all of the following conditions. Vmax must be greater than VOC or VT, and Imax must be greater than ISC or IT. Additionally, CA must be less than the sum of CI and cable, and LA must be less than the sum of Li and La cable. All these conditions are noted on the loop schematic, also known as the control drawing.
Now, let's look at the parameters for the associated apparatus, or the barrier. VOC or VT is the maximum open circuit voltage that the associated apparatus, barrier, can have under fault conditions. When using multiple associated apparatus, FM uses the voltage combination value, VT, instead of VOC ISC, or it is the maximum short circuit current that the associated apparatus can deliver under fault conditions. And for multiple associated apparatus, FM uses the current combination value, IT, instead of ISC. CA refers to the maximum capacitance that can be safely connected to the associated apparatus, and LA refers to the maximum inductance that can be safely connected. Cable and La cable are the capacitance and inductance of the connecting cable, respectively. All these entity parameters are specified on the loop schematic or control drawing. The entity concept is used by FM and UL, and is also used by CSA upon request. On the other hand, the parametric concept is used only by CSA.
I'll now introduce the parametric concept, which is exclusive to CSA, and the loop schematic. In the parametric concept, 2 values are defined for intrinsically safe apparatus. First is the maximum hazardous location voltage that may be connected to the apparatus, and second is the minimum resistance of the barrier that may be connected to the apparatus, measured in ohms. Additionally, CSA may directly investigate specific barriers and list those results on the loop schematic along with the parametric rating. NEC Article 504 specifically requires that intrinsically safe and associated apparatus have a control drawing, which details the allowed interconnections between the intrinsically safe and associated apparatus. This control drawing is also referred to as a loop schematic, and its drawing number is referenced on the apparatus nameplate so that the user can verify it.
Let's go over the items that must be included in the control drawing, or loop schematic. First is the wiring diagram. The drawing must contain a diagram of the apparatus showing all intrinsically safe terminal connections, and for intrinsically safe apparatus, all associated apparatus must be defined either by specific equipment identification or by entity parameters. Second are the entity parameters or system parameters in the case of CSA, which must be presented in a table showing allowable values for each applicable class and group. Third is the hazardous location identification. A demarcation line must be drawn on the schematic to distinguish between equipment in the hazardous location and equipment in the non-hazardous location, and the class, division, and group of the hazardous location must be specified. Fourth is equipment identification, where the equipment must be marked with the model and part number, etc., to allow for positive identification.
I'll now cover the Division 2 requirements and an overview of protection techniques. First, for Division 2, the installation requirements for FM-approved equipment must be shown on the drawing. Now, we will move on to comparing different protection techniques. The first technique we'll cover is the explosion-proof technique, which is implemented by enclosing all electrical circuits within housings and conduits. These housings and conduits are designed to be strong enough to contain any explosion or fire that may occur inside the equipment.
I would like to introduce the advantages and disadvantages of the explosion-proof technique among the protection methods for hazardous areas. Explosion proofing is a method of enclosing all electrical circuits within a sufficiently sturdy housing and conduit to contain any explosion or fires that may take place inside the apparatus. Looking at the advantages, first, users are familiar with this technique and understand its principles and applications. Also, sturdy housing designs provide protection to the internal components of the apparatus, allowing their application in hazardous environments. And an explosion-proof housing is usually weatherproof as well. On the other hand, there are clear disadvantages. Before housing covers may be removed, circuits must be de-energized or the location rendered non-hazardous, and opening the housing in a hazardous area voids all protection. Additionally, this technique generally requires the use of heavy bolted or screwed enclosures. Finally, regarding installation, the user has responsibility for following proper installation procedures.
I will now cover the installation requirements for the explosion-proof technique and provide an overview of the intrinsically safe technique. Explosion-proof installation requirements are listed in Article 501 of the NEC, or Article 18 to 106 of the CEC, and local and national electrical codes must be followed. All electrical wiring leading to the field instrument must be installed using threaded rigid metal conduit, threaded steel intermediate metal conduit, or Type MI cable. Also, to maintain the explosion-proof rating and reduce the pressure piling effect on the housing, conduit seals may be required within 18 inches of the field instrument. Next is the intrinsically safe technique. This technique operates by limiting the electrical energy available in circuits and equipment to levels that are too low to ignite the most easily ignitable mixtures of a hazardous area. An advantage is that this technique offers lower cost, as no rigid metal conduit or armored cable are required for field wiring of the instrument.
I would like to introduce additional advantages of the intrinsically safe technique. First, it offers greater flexibility because this technique permits simple components such as switches, contact closures, thermocouples, RTDs, and other non-energy storing instruments to be used without certification, provided they have appropriate barriers. Ease of field maintenance and repair are also advantages. There is no need to remove power before adjustments or calibration are performed on the field instrument. In terms of safety, the system remains safe even if the instrument is damaged, because the energy level is too low to ignite most easily ignitable mixtures. However, one point to note is that diagnostic and calibration instruments must have the appropriate approvals for hazardous areas.
I will now discuss the disadvantages of the intrinsically safe technique, followed by the dust ignition-proof technique. A disadvantage of the intrinsically safe technique is that it requires the use of intrinsically safe barriers to limit the current and voltage between the hazardous and safe areas to avoid the development of sparks or hot spots in the circuitry of the instrument under fault conditions. Also, because the energy is limited at the source or barrier, high energy consumption applications are not applicable to this technique. Therefore, this technique is limited to low-energy applications such as DC circuits or electropneumatic converters, also known as I/P converters. Next, the dust ignition-proof technique results in an enclosure that will exclude ignitable amounts of dusts. This enclosure ensures that arcs, sparks, or heat generated inside the enclosure do not cause ignition of exterior accumulations or atmospheric suspensions of a specified dust on or near the enclosure.
I would like to introduce the definition and advantages of the non-incentive technique. The non-incentive technique allows for the incorporation of circuits in electrical instruments that are not capable of igniting specific flammable gases or vapor and air mixtures under normal operating conditions. Looking at the advantages, This technique uses electronic equipment that normally does not develop high temperatures or produce sparks strong enough to ignite the hazardous environment. Also, there is lower cost than other hazardous environment protection techniques because there is no need for explosion-proof housings or energy-limiting barriers. Furthermore, for non-incentive circuits, the NEC permits any of the wiring methods that are suitable for non-hazardous locations. At the end of this chunk, a table of overseas certification agencies begins, organized by location, abbreviation, and agency, starting with the United Kingdom.
Next, we turn to global protection.
I would like to introduce the major certification agencies outside of North America, specifically in Europe and the Asia-Pacific region. This table organizes the abbreviations and agency names by location. For the UK, it is BSIFA, the British-approved service for electrical apparatus in flammable atmospheres. Germany is handled by PTB, the Physikalisch-Technische Bundesanstalt. France is LCIE, the Laboratoire Centrale des Industries Électriques. Australia is SAA, the Standards Association of Australia. And Japan follows in the subsequent items of this table, featuring agencies such as TISAZA, the Japan Technical Institute for Industrial Safety.
I would like to introduce the Senelec approval system, which serves as the standard for explosion protection certification in the European market. Senelec stands for the European Committee for Electrotechnical Standardization, and these standards apply to all EU member states and other countries that choose to adopt them. When a piece of equipment successfully passes the tests according to the relevant Senelec standard, it receives Senelec approval. Testing can be performed at any recognized testing laboratory within Europe. While approvals may be based on national standards, Senelec approvals are generally preferred in practice. Meanwhile, regarding the disadvantages of the non-incentive technique, this technique is limited to Division 2 applications only, and there are constraints on the control room side to limit the energy going to the field wiring. In other words, it must be designed so that if the field wiring is open, shorted, or grounded during normal operation, the resulting arcs or sparks will not have enough energy to cause ignition.
Now, I will introduce the approval agencies and types of protection used in regions outside North America, specifically in Europe and the Asia-Pacific region. First, regarding the non-incentive technique mentioned earlier, please note that more stringent labeling may be required for both the field instrument and the control room device. In these regions, there are approval agencies common to each country and specific types of protection they utilize. A representative example is flameproof. Flameproof protection uses a structure that can withstand the pressure developed during an internal explosion of an explosive mixture within an enclosure. It prevents the explosion from transmitting to the surrounding explosive atmosphere and operates such that the external surface temperature is maintained low enough not to ignite surrounding explosive gases or vapors.
Following the flameproof protection method, it is important to note that this is similar to what North America calls explosion-proof, and the IEC refers to it as XD. Next, I will introduce increased safety. Increased safety is a protection method applied to electrical apparatus that do not produce arcs or sparks in normal service. It involves applying various measures to the internal and external parts of the device to reduce the probability of excessive temperatures or the occurrence of arcs and sparks. This method can be used in combination with flameproof protection and is denoted by the IEC as XE. Additionally, labels indicating hazardous area approval are displayed as a combination of the explosion protection symbol, protection type, gas group, and temperature code, such as XIA-IICT4.
I will now discuss the nameplate marking regulations for Senelec approvals, as well as the IEC's intrinsically safe and non-incentive protection methods. Equipment with Senelec approval must include the explosion protection symbol on the nameplate. This mark indicates compliance with Senelec requirements and is recognized by all EU member states. Next, intrinsically safe protection is a method where electrical equipment, under both normal and abnormal conditions, is incapable of releasing sufficient electrical or thermal energy to cause ignition of a specific hazardous atmospheric mixture in its most easily ignitable concentration. The IEC denotes this as XI. Finally, non-incentive protection is a method where equipment is incapable under normal conditions, of causing ignition of a specified flammable gas or vapor and air mixture due to arcing or thermal effects, and the IEC denotes this as XN.
I would like to introduce the classification method used by approval systems that follow IEC nomenclature. Agencies such as BSIFA, LCIE, PTB, and SAA use IEC nomenclature to classify equipment for hazardous locations based on 3 items: type of protection, gas group, and temperature code. Looking at the protection type symbols, IA refers to intrinsic safety allowing 2 faults, and IB refers to intrinsic safety allowing 1 fault. D stands for flameproof, and E stands for increased safety, lowercase, and denotes type and non-incentive, which is a notation specific to SAA, while uppercase, and denotes type and non-incentive, specific to BSIFA. Hazardous locations outside North America are classified by gas group and zone. In terms of group classification, electrical equipment is divided into 2 groups. Group I covers electrical equipment used in mines, and Group 2 covers all other electrical equipment. Group 2 is further subdivided into 3 subgroups, A, B, and C. The specific hazardous materials within each group can be found in the Senelec EN 60000 and 79-0 standard.
I'd like to introduce which materials are covered by each IEC gas group and the compatibility rules between subgroups. The automatic ignition temperature for each material can be found in IEC 60000 and 79-4. First, Group I is for mining, covering atmospheres containing methane or gases and vapors of equivalent hazard. Group IIA covers atmospheres containing propane or gases and vapors of equivalent hazard. Group IIB covers atmospheres containing ethylene or gases and vapors of equivalent hazard. And Group IIC covers atmospheres containing acetylene or hydrogen or gases and vapors of equivalent hazard. There's an important compatibility rule here. An apparatus approved for any subgroup in Group 2 may be used in the subgroup below it. For example, equipment approved for Group IIC may also be used in Group IIB locations.
I'd like to introduce Zone 00 and Zone 11, which are used to classify hazardous locations in regions outside of North America. Zones are distinguished based on the probability that hazardous materials are present in the surrounding atmosphere in an ignitable concentration. First, Zone 0 refers to locations where an explosive concentration of a flammable gas or vapor mixture is continuously present or present for long periods. While Zone 0 is not specifically defined on its own, it is contained within the North American Division 1-1 classification and represents the area with the highest probability that an ignitable mixture is present. Next, Zone 1 is a location where an explosive concentration of a flammable or explosive gas or vapor mixture is likely to occur in normal operation. Zone 1 also falls within the scope of the North American Division 1 classification. In summary, the key point is that North America uses the division system, while other regions use the zone system to express the hazard level of a location.
Now, I'll introduce the basic concepts of Zone 2 and temperature codes. Zone 2 is a location in which an explosive concentration of a flammable or explosive gas or vapor mixture is unlikely to occur in normal operation and, if it does occur, will exist only for a short time. You can consider Zone 2 to be basically equivalent to the North American Division 2 classification. Moving on to temperature codes, a mixture of hazardous gases and air can be ignited simply by coming into contact with a hot surface. The conditions under which a hot surface ignites a gas depend on the surface area, surface temperature, and the concentration of the gas. Therefore, approval agencies test and establish maximum temperature ratings for each piece of equipment submitted for approval. Group 2 equipment that has undergone this testing is assigned a temperature code that indicates the maximum surface temperature attained by the equipment.
Here, I'll introduce the reference ambient temperature used when determining IEC temperature codes. Temperature codes are basically calculated assuming an ambient temperature of 40 degrees Celsius, or 104 degrees Fahrenheit. However, if a higher ambient temperature is specifically indicated, that indicated value is used as the basis. Based on these criteria, the IEC temperature codes from T1 to T6 are defined. Please remember that the assumption of the ambient temperature is a prerequisite for evaluating the maximum surface temperature of the equipment.
Now, I'll introduce the IEC temperature codes and an overview of the IP codes for enclosures. IEC temperature codes consist of 6 levels: T1, T2, T3, T4, T5, and T6, and each code specifies the maximum allowable surface temperature in degrees Celsius and Fahrenheit. Next, the degree of protection for enclosures is indicated by the IP code according to IEC 60529, 60,529. IP is an abbreviation for ingress protection. This code consists of the letters IP followed by 2 characteristic numerals, which indicate whether the equipment conforms to the desired level of protection. Ultimately, the IP code is a means of expressing how well an enclosure prevents the ingress of foreign objects or water in a standardized way.
I'll now explain the meaning of the 2 digits that make up the IP code. 2 characteristic numerals follow the IP letters, for example, as in IP 54, 54. The first numeral indicates 3 types of protection: protection against human contact with or approach to live parts, protection against human contact with moving parts inside the enclosure, and protection against the ingress of solid foreign objects. The second numeral indicates the degree of protection the enclosure provides against the ingress of water. By combining these 2 numbers, the protection performance against both solids and moisture is expressed together in a single code.
Now, I would like to introduce the definition table for IP code numerals and a detailed comparison between NEMA and IEC enclosure ratings. First, the first numeral represents protection against solid bodies. 0 means no protection, 1 is protection against objects greater than 50 millimeters, 2 is for objects greater than 12.5 millimeters, 3 is for objects greater than 2.5 millimeters, 4 is for objects greater than 1 millimeter, 5 is dust protected, and 6 means dust type. The second numeral represents protection against liquids, specifically water. 0 means no protection, 1 is vertically dripping water, 2 is angled dripping water between 75 and 90 degrees, 3 is sprayed water, and 4 is protection against splashed water. Following these, 5 means jetting, 6 is powerful jetting, 7 is temporary immersion, and 8 is protection against permanent immersion. Next, this book provides a comparison table for converting NEMA type numbers to IEC IP ratings. Finally, please note that the flame-proof technique, among explosion-proof methods, is implemented by enclosing all electrical circuits in housings and conduits strong enough to contain any explosion or fires that may occur inside the apparatus.
Now, I will introduce the advantages of the flame-proof technique and the conversion from NEMA to IEC IP codes. The first advantage of the flame-proof technique is that it is a method already familiar to users. Its principles and applications can be understood intuitively. Second, sturdy housing designs physically protect the internal components of the apparatus, enabling their application in hazardous environments. Next, a conversion table for translating NEMA type numbers to IEC IP ratings is provided. There is a point of caution here. NEMA types are designed to meet or exceed the test requirements of the associated IEC classifications. In other words, NEMA ratings are more stringent than or equal to IEC ratings. For this reason, this conversion table can only be used in one direction, from NEMA types to IP codes, and cannot be used to convert IP classifications back to NEMA types. The title of the table is Conversion of NEMA Types to IEC IP Codes.
I will go over the specific values in the conversion table we just saw. NEMA Type 3 corresponds to IP14, Type 3S to IP54, and Type 4 and 4X to IP65. These codes are called Ingress Protection Codes, or IP codes. Flame-proof housings typically possess waterproof performance as well, making them advantageous for outdoor environments. Next are the disadvantages of the flame-proof technique. First, before removing housing covers, the circuits must be shut off or the location must be rendered non-hazardous. Second, the moment the housing is opened in a hazardous area, all protection is voided. Third, there is the burden that heavy bolted or screwed enclosures generally must be used. Next, I would like to introduce the increased safety technique. This method applies special measures to reduce the probability of excessive temperatures and the occurrence of arcs or sparks during normal service.
Let's start with the advantages of the increased safety technique. First, increased safety enclosures provide at least IP54 enclosure protection. Second, installation and maintenance are easier compared to the flameproof method. Third, wiring costs can be significantly reduced compared to flameproof installations. However, there are disadvantages. This technique is limited in the apparatus for which it may be used, and is normally limited to devices such as terminal boxes and compartments. Next, I will introduce the intrinsically safe technique. This method uses intrinsically safe barriers to limit the current and voltage between hazardous and safe areas. The purpose is to prevent the development of sparks or hot spots in the circuitry of the instrument under fault conditions. An advantage of the intrinsically safe technique is that it costs less because the rules for field wiring of the apparatus are less stringent.
Continuing with the advantages of the intrinsically safe technique, it offers greater flexibility. Simple components that do not store energy, such as switches, contact closures, thermocouples, and RTDs, can be used with appropriate barriers without special certification. Additionally, field maintenance and repair are easy. This is because there is no need to shut off the power before adjustments or calibration are performed on the field instrument. Even if the instrument is damaged, the system remains safe because the energy level is too low to ignite even the most easily ignitable mixtures. However, diagnostic and calibration instruments must have the appropriate approvals for hazardous areas. There is also a disadvantage. Since energy is limited at the source or the barrier, this technique cannot be applied to high energy consumption applications.
Intrinsic safety techniques are limited to low-energy applications, such as DC circuits and electro-pneumatic converters. Next, I would like to introduce the Type N technique. This technique involves incorporating circuits into electrical instruments that are not capable of igniting specific flammable gases or vapor and air mixtures under normal operating conditions. One thing to note is that the Type N protection method is not available from Senelec. Let's look at the advantages of the Type N technique. First, it uses electronic equipment that normally does not develop high temperatures or produce sparks strong enough to ignite the hazardous environment. Second, the cost is lower than other hazardous environment protection techniques because there is no need for flameproof housings or energy-limiting barriers. Third, it provides a degree of protection of IP54. On the other hand, a disadvantage is that this technique is applicable to Zone 2 locations only.
Finally, I would like to introduce the remaining constraints of the Type N technique. This technique places constraints on the control room to limit the energy supplied to field wiring. In this context, normal operation refers to states where field wiring is open, shorted, or grounded. These constraints are implemented so that arcs or sparks occurring during normal operation will not have enough energy to cause ignition.